Question 6.2 is a bit trickier than 6.1. It combines a lot of what we've covered in lectures 4, 5 and 6 into one question. So there's quite a bit to get through, but it's a simple question in the way it's asked. You've got a bar and points A and B are the end points of the bar, and you're applying a force at one end. And it's just asking first of all, what's the angular acceleration of the bar, and what is the magnitude of the acceleration at the various points along it, so point A, point B, and the centre of mass. And we can assume it's a uniform bar, so it's a constant density bar, so the centre of mass is halfway along. So if you apply a force, then what is the acceleration at different points? So let's start by drawing a sketch of the bar with A and B, and then the centre of mass also labelled, supposed to be halfway along. And we've got this force F, which is given in the question as being equal to 15 newtons. Right? And that is equivalent, and here I'm going to refer to our notes at the end of lecture 6 so this is general planar motion. You've got some object, some rigid body which has a centre of mass there, and you apply a force that's not at that centre of mass. Then you can decompose that into a fixed axis rotation around the centre of mass plus a translation of the centre of mass. So that's why knowing the centre of mass makes it very convenient. And the summary slide says a force on a body is equivalent to the same force moved a perpendicular distance r plus an additional torque. So let me draw this again. Plus. And this is, by the way, 30 degrees to the horizontal. It's 30. And so this is saying that this is equivalent to a force at the centre of mass, F, plus a torque. And here we've moved the force a perpendicular distance here of, or how far have we moved it, that distance there is L over 2 times cos 30. So that, because that's L over 2. So that is force times by L over 2 cos 30. So that's essentially what we've done there. We've decomposed this force, which is not acting at the centre of mass, to a force that is acting at the centre of mass plus a torque. And the magnitude of that torque is equal to how far you've moved the force perpendicular to the direction in which that force is acting. So that's just resolved L over 2 horizontally here. And what that can tell us straight away is that if we know what the moment of inertia is, we can work out what the angular acceleration of the body is, because T equals I alpha. And that was from lecture 6. That's Newton's second law in rotation. And we are conveniently told in the question that we can calculate this moment of inertia of a bar around its centre of mass as equaling, so really I should put subscript Cm to denote that this is the moment of inertia around the centre of mass, because if you could take different axes of rotation, and that's equal to 1 over 12 times its mass times the length squared. So from the question we're told that the mass is 4 kilograms and the length is 20 centimeters. So our moment of inertia is 1 over 12 times 4 times 0.2 squared, 0.0133 kilogram meter squared. So we've got the moment of inertia. We know what the torque is around the centre of mass, therefore we can work out what the angular acceleration is. Just by rearranging that. And if we put in, so I'm now going to calculate F dot L over 2 cos 30, all divided by 0.0133. So the force is 15 newtons given the question, times 0.2 over 2, so the length is 0.2, divided by 2, times by cos of 30, which is square root of 3 over 2. And that is all divided by the moment of inertia, which is 0.0133. That gives us our angular acceleration of 97.7 radians per second squared. And that's the first part of the question. So by splitting it up in this way, we've worked out what the torque is around the centre of mass, and because we know the moment of inertia around the centre of mass, we've been able to work out what the angular acceleration is at this instant. That's the easy part. Part B is more difficult, and let's focus on calculating the magnitude of the acceleration at A. So that's this point here. And we don't know exactly where it's going to be, but if you imagine this is your bar and we apply a force here, you can see that actually this point goes the opposite direction to the point of application. So we might expect, depending on how what the force is and how long it acts for, that the acceleration is actually in this direction. But we don't know yet. That's what we're going to find out. So let me just put a bit more detail on these figures here. So now we're going to go to our summary slide for lecture 5, and we're going to use this equation. But instead of B and A, we're going to switch the subscript. So actually what we're going to be trying to solve is the acceleration of A, this point here, is equal to the acceleration of the centre of mass plus the acceleration of A relative to the centre of mass. So this is that acceleration there. That's the acceleration of A relative to the centre of mass, because we've now decomposed this into a fixed axis rotation here, if you see. And that has two components. It has a tangential component and it has a radial centripetal component. So that's the centripetal component, and that is the tangential component. So let me just draw those in. And this is the acceleration of A relative to the centre of mass in the tangential direction. And that is the total, that is the resultant of those two. So it's just the acceleration of A relative to the centre of mass. Okay, so hopefully that's clear. And we're going to try and find out what the acceleration of A is by working out what these individual components are. Now this first component here, that's easy, because the acceleration of the centre of mass, the only thing that's contributing to the centre of mass is this part of the sum here, because this is a fixed axis, so that's not accelerating at all. And so what we have here is just a translational acceleration. So this is just force divided by mass. So this is Newton's second law in translation. So the acceleration of the centre of mass, so the magnitude of it, is just equal to F over m. So the force is, go back to the question, 15. The mass is 4, so that's 3.75 meters per second squared. Okay, so now we can work out what the magnitudes of these components are. So the magnitude of the acceleration of A relative to the centre of mass in the tangential direction is equal to, now if we go back to our notes from lecture 5, the magnitude is r, where r is the radius of rotation, times by the angular acceleration. The radius of rotation in this case is L over 2. So this is r alpha, so it's L over 2 is r. Our alpha, we worked out here, is 97.7. So let's do that. That's L over 2, so 0.2 divided by 2 times by 97.7 gives you 9.77 meters per second squared. Now the next component, so we've just worked out what the magnitude of this is. We're going to work out now what the magnitude of the centripetal part is, and to do that we need to know what the angular velocity is. So this is what we're trying to calculate. This is, again from our notes, this is the radius of rotation multiplied by omega squared. The radius of rotation is just L over 2. And the angular velocity at this instant is just told, given to us in the question, is 5 radians per second. So omega is 5. So omega squared is 5 squared. So this is going to be 0.2 divided by 2, so the length divided by 2, times by 5 squared. Is that right? Yeah. That's 2.5 meters per second squared. Okay, so we've now got the magnitudes of each of these three components, and they are there. Now I could construct a sort of elaborate vector polygon to work out what the acceleration of A is, but actually in this case it's easier just to resolve in the two directions. So we're going to, let's say this direction is y, and this direction is x. And I'm going to work out what the two components of the acceleration of A are, and then combine them to get the magnitude. So the acceleration of A in the y direction, let's go vertically first of all. Well, what is the y component of the acceleration of the centre of mass? Well, it's in the direction of y, so it's equal to 3.75. So that's the acceleration here of the centre of mass, which is equal to 3.75 meters per second squared. I'm just going to write, just to make it a bit simpler, just write down that's equal to 9.77, and that's equal to 2.5. So we've got 3.75 going upwards, and the y component of this vector, well, we've now got to resolve it this angle here, and that angle is going to be 30, because that angle is 30. So you can't read that very easily. Let's make that a bit bigger. That angle is 60. So we've now got an acceleration that is in the negative y direction, so it's 9.77 that we've got to resolve through this 30-degree angle. So that's going to be minus 9.77 cos 30. We've also got to resolve this component vertically, and again this is a negative component because it's in the negative y direction, so this will be minus 2.5 cos 60. And let me just put that in, 3.75 minus 9.77 times square root 3 over 2, that's cos 30, minus 2.5 times 0.5, cos 60 is 0.5. So that gives us overall a negative component of minus 5.96 meters per second squared. So now let's calculate the x component of the acceleration of A, and the translational component doesn't contribute because we're looking in the component in this direction, but these two, so the two x components from these two vectors do. So we've got the acceleration of A relative to the centre of mass in the tangential direction is 9.77, and if we resolve that in horizontally, so in this direction, we've got to resolve around an angle of 60, and it's going to be a negative value because we're resolving it in negative x. So that's minus 9.77 cos 60. And then you've got this component, which is resolved through 30 degrees, so that's 2.5 cos 30, and that's positive. So that is equal to minus 9.77 times 0.5 plus 2.5 times square root 3 over 2. That's minus 2.72 meters per second squared. So finally then, to get the acceleration, the magnitude of the acceleration of A, then we just use Pythagoras. Square root of 5.96 squared plus 2.72 squared, 500 squared plus 2.72 squared equals 6.55 meters per second squared. So that's the magnitude of the acceleration of A here. And we've worked out that they're both negative components, so direction is going to be down here somewhere. Now I won't do the same for acceleration of B because it's essentially the same procedure, but your acceleration of B is over here somewhere. That's it then.